Hi everyone. In this video, this will actually be quite a short video, but I would like to share to you another proof to the centripetal force formula. However, this is without calculus, and it is a very short proof, simply based on the idea of, I won't say a limit, but how small changes in theta affect a small change in sine of the function. So here I've drawn a circle for a circular motion with a radius r, and we know that the magnitude of the velocity throughout circular motion stays the same. And so I will quickly write that here. I'll write that in blue. So we can remember this, v is constant. So in fact I will just I've named two vectors here, v1 and v2, let them be to just mod of v, okay? In fact, let's just call it v itself. So at 2 points during this motion, we can look at the velocity, and we can see that if they're theta apart, just by doing some simple trigonometry, that we know this here is a 90 degrees between the v2 and the radius, the green radius, which I've drawn. And if we extend this line, black dotted line, we can see that this angle theta, in fact I can just quickly show it here, this angle theta, we can see that if we have this here, we have a theta here, like that this is pi by 2 minus theta, this here, and hence, because we know this is perpendicular, we know all of this is 180, and so this is also theta. And that's the basic idea behind it, just behind why we say that is theta. So now let's delve into the proof. All we need to do is we just need to model these as vectors. The velocities are of course vectors. So let's let v1, it has a 0i component plus the magnitude of the velocity, j hat. Our v2 is just, meanwhile our v2 is minus, as we can see here, it's minus sine, so minus v sine theta I hat and then plus v cos theta. Let's zoom in so we can read this a bit better. V cos theta j hat. We've just modeled these as vectors, and actually we're almost there. All we need to do is we just need to use what we know of acceleration. And we know, let's start like this. Let's do it even easier. All we can do is we can say this. Therefore, the delta v, change in velocity, is equal to minus v sine theta I hat. We can just write the mathematics here quickly. So v2 minus v1 2 minus v sine theta I hat, because the I component of v1 is 0, plus v cos theta minus v times j hat. Now we have to use some reasoning here. It's very basic. All we can say, we know this, that as the theta tends to 0, we know that sine of theta tends to theta itself, and cos of theta tends to 1. And so basically all we can say, and I'll explain why we did this once we get there. So we can say minus vi plus v times 1 theta, v theta I, plus v times 1 minus v, which will just be 0. So minus v theta I, that's all we get. So as now we know what acceleration is. Acceleration is equal to delta velocity over delta t, average acceleration actually. So we can just say implies acceleration is equal to minus v theta, and we're assuming theta to be the change in angular displacement here over t, the time interval in which this happens. So if we take the, let's take the, we can just look at this quickly, and as we know, as omega is equal to delta theta over delta t, and we know these are this change in time and change in angular displacement, all we have to do is we can just do a minus v omega I implies the mod of a, so vector of course is equal to v omega, as v omega is equal to v over r. Therefore AC is equal to v square over r, and that's our AC, which is the centripetal acceleration, and from this we know as sum of force is equal to ma implies Fc is equal to mv square for r. You can notice we also can write this in terms of v in terms of omega, and then we get omega square over omega square r, and so we can also write this as omega square r as well. So thank you for watching. If you like this video, please don't forget to like, share, and subscribe, and I hope to see you next time.